What's up, math scholars and math haters? This is Mr. W. Today we're going to do something a little bit different, and today we're going to go over the rule for divisibility by sevens, how to use it, and how we can actually know that it's true. So to start with, I just want to demonstrate this rule with the number 343. Now I picked this number specifically because it is equal to 7 times 49, so I know it's a multiple of 7 already. But I'm going to go ahead and demonstrate this trick very quickly here. So if you see that I have the steps written here on the right, first step I call split. That basically means that I'm going to take this number 343 and I'm going to split it so that the ones digit, the 3, is separate from the rest of the number. Now it doesn't matter if this number has 3 digits, 2 digits, or 1,000 digits. For divisibility by 7, I'm only interested in splitting the number off at the ones digit. So next step is to take this ones digit and actually double it. So I'm going to take 3, multiply it by 2, and I get 6. Step 3, I need to take that doubled ones digit and I need to put it under the rest of this number. So in this case, the 34 tens, I need to put it under the rest of that number and do a quick subtraction problem. So this will end up becoming 34 minus 6. And as I subtract 34 minus 6, I'm going to just go ahead and do it, so I get 28. And now I go to my final step, which is to check if my answer is either 0 or a multiple of 7. Now, this could be positive or negative. You might end up getting some negative numbers sometimes if you do this enough. But the number 28, we are absolutely okay because the number 28 is equal to 7 times 4. So that's a quick demonstration of the rule. The basic idea is we split the number at the ones digit, multiply that ones digit by 2, subtract that doubled ones digit from the rest of the number, not from the original number, and then we check the answer to that subtraction problem to see if we got a multiple of 7. Since we got a multiple of 7 for the answer, that's another way to confirm that the original number we were testing is also a multiple of 7. Now, the point of this for my class was actually to look at the proof of this rule. And this will be instructive for a couple of reasons. But I want to start by just thinking about what exactly we're proving. Now, I have the number 343, and I have it split up into its ones digit and the rest of it, what we would call the tens. Now, the fact that I'm calling this the tens is actually very important, because we're actually going to find two ways, or two expressions that, or one would express the original number, the other one would express what happens when we do the steps. And then we're going to actually have to prove that if one of those is divisible by 7, then the other one is divisible by 7, and vice versa. So if I take my 34 tens and my 3 ones, I'm just going to go ahead and I'm going to call my tens x, and I'm going to call my ones y. So if x is 34 and this represents tens, then I would have to write this number as 10x. And then the ones digit is something I can just add on its own, so I can go ahead and call this plus y. Now, I need to add something else. This deals with a very quick unit that we've done on something called mod. Now, the idea of mod is like dividing and finding the remainder. Your mod is the same as your remainder. And what we're trying to prove is that if this expression would give us a remainder of 0 under mod 7, and if you're my students, you should have seen this notation before, then the other part of this, where we have already split the number, and we take the left digits of it, so in this case x, and we subtract double that ones digit, so double what y was. Basically, I'm trying to prove that if this is divisible by 7, then so is this. If the original number is divisible, then so is what happens when we do split, double, and subtract. So if you're my student and you're filling out the half sheet I have to go along with this, this should be one of your questions. What are the two statements we're trying to prove? Here they are. If 10x plus y is equivalent to 0 under mod 7, then x minus 2y is also equivalent to 0 under mod 7. And I do want to also talk about what an if and only if proof means. Another way you might see this written, and this is going to be exceptionally lazy, but mathematicians are exceptionally lazy. If you ever see if with 2 f's, that's what this means. And when we talk about an if and only if proof, that essentially means we need to prove it both ways. We need to prove that if the left statement is true, then the right statement is true, and also that if the right statement is true, then the left statement is true. So this proof is going to have two parts. One part, I'm going to start here and end up over here. For the other part, I'm going to start over here and end up back here. So that's essentially where this proof is going. So let's go ahead and start with the actual proof. So let's suppose that I have a number 10x plus y. Now I'm expressing this number in this way because it makes it easier to visualize splitting it up between its leftmost digits and then the ones digit that's here on the right. All right, so I'm going to use a few little tricks that we can use in mod equations in order to actually finish out this proof. So to start with, I'm going to subtract something from both sides. I'm going to subtract y. And where this is going to get me is it's going to get me to where I have 10x on the left, and then I have negative y on the right. All right, so I just subtracted something from both sides. That's something we do in any equation. Only difference is I did it with a letter and I did it in a mod problem. Now, I'm going to get into something that we can't do in a regular equation. I am going to add something to just one side. Now, the key with this is the thing that I'm adding to just one side is a multiple of 7, is a multiple of this mod number. I can do that. That's a really weird rule that, like I said, only applies to these mod proofs, but it's something that I can do. So I'm going to add plus 21y. Now 21 is a multiple of 7, therefore 21 times any y number, which we already know just from the fact that it's a ones digit, is a whole number. We know that this whole thing is a multiple of 7, so again, this is okay. Where this gets me is that 10x is equivalent to 20y under mod 7. And now I'm going to go back to a more familiar step in working with equations. I'm going to do the same thing to both sides of the equation. Specifically, I'm going to divide the left side and the right side both by 10. Now, technically, this fraction bar should go under everything. It's just a little easier for me to visualize this if I keep it under the numbers. So where this leads us is 10 divided by 10 cancels, and this leaves us with just x. 20 divided by 10 leaves us with 2, and then we keep the y there. So now we're left with x is equivalent to 2y. And the last thing that I'm going to do is go back to subtracting. I'm going to subtract 2y from both sides, and this is going to give me that x minus 2y is equivalent to 0 under mod 7. And remember, we only got there because we knew that our original number was equivalent to 0 under mod 7. So now for the other step. Now for the other side of the proof. And the steps to this are actually pretty much going to be the opposite of the other steps. So if I start with x minus 2y is equivalent to 0 under mod 7, the very first thing I'm going to do is I'm going to add 2y to both sides, which gives me x, because negative 2y and positive 2y cancel, is equivalent to 2y. Next thing I'm going to do is I'm going to multiply by 10. So this gets me 10x is equivalent, sorry about that, 10x is equivalent to 20y. Next thing I'm going to do is take away 21y from just the right side. Again, this is something I can do. 21 is a multiple of 7, and anything that's a multiple of this mod number is okay to subtract or add to just one side. Gets me to 10x is equivalent to negative y. And finally, for the last step, I will just add y to both sides, leading me back to the original statement, 10x plus y is equivalent to 0 under mod 7. Now again, the key with this kind of proof is that we went both ways. Even if the steps are exactly the same or exact opposites of each other, and we essentially did them in the opposite order, this is still an important type of proof that if you go further in math, you will have to come across.